Hey everyone, I know we all went on a big hike, so I'm gonna try to take this like a little bit slower and a little bit fun. I'm gonna request some audience participation coming up. And I guess not knowing that this was going to be before the hike, I was originally gonna talk about differential geometry and stuff like that, but given that this was after the hike, we're gonna talk a little bit about some slightly different things. We're going to talk about symmetry, how to understand symmetry. We're going to talk about like a sort of combinatorial way of understanding symmetry groups, and we're going to then use that to try to understand how curvature and topology are related. But the only math that I'm going to ask you to do, so you're going to need to know three things. One, that a circle has 360 degrees in it. You're going to need to know a little bit about counting and math with or like arithmetic with integers. And let's see, the third thing, I can't even remember what the third thing is right now. Yeah, I think we just need to know how to count basically. And maybe like add and subtract fractions. So that's what I'm going to be asking of you, and we'll kind of do that ourselves. So that's what's going on. So to start out with, I'll give you a definition of symmetry. So symmetries are transformations, so like motions that leave an object looking the same. And so a lot of what I'm going to be talking about is from this book, The Symmetry of Things, which is by Heidi Burgett, John Conway, and Chaim Goodman-Strauss. And I put these in proper mathematical author ordering, which John Conway did not allow them to do. He wanted his name first. So, but this is, I'm going to be teaching you about a thing that has a really fancy mathematical name, but is a really fun and kind of universal concept, and it's called an orbifold. So I'm going to scare you away with that first, and then walk it all back and talk a little bit about how they're actually friendly. So first, we're gonna start simply and have a look at some flags from around the world. So these are a bunch of different flags, and what we're going to assume is that there isn't a rectangular border, that the flag extends infinitely far away. So whatever the background is, you can just continue that indefinitely. So looking at these different flags, what sort of symmetries do you see?
Mirror.
So is mirror symmetry?
It's rotational.
There's rotational symmetry. When you, I'm gonna pick on maybe different people. So someone says mirror, someone says rotational. Can you, yes? Pardon? Inversion symmetry. Yes, so I think that's well, I think we would call that mirror symmetry as well. I think I'm gonna use that wording the same way. So I guess for I'm gonna use your ideas, but then ask other people to answer this. So where do you see mirrors on these? Well, I mean, you can use words to describe it. I know
All of them have people? All of those flags can have mirrors?
Yeah, all of the flags can have mirrors. Do you?
Definitely Albania between the two heads.
Yeah, so Albania has this like nice symmetry line through here. Anyone else? Any other symmetries?
Are we talking about 3D or?
Right now, these are just 2D, and
We
they're
don't think about.
yeah. Right now, we're not going to think about 3D, and it's going to and just like of these like motifs on an infinite plane.
Okay.
The Tennessee one, if we go through one of the stars and in the middle of the two others, it gives you three symmetries.
Yeah, so there's 3 mirrors in Tennessee. That's great. So there's a mirror that goes through here, a mirror that goes through here, and then a mirror that goes through here. Excellent.
Maybe Georgia like two kind of symmetric here and here.
Yeah, Georgia has 2 symmetric mirrors. So there's one through the center, top to bottom, and one through the center, left to
I
right.
think we could like divide this one white. It could also have like different symmetric,
If you could,
the white part.
if you could, yeah, so each of the white parts has its own set of special symmetries, but yeah, so the white parts actually look quite a lot like Switzerland, only backwards.
And also got diagonals. You can mirror the diagonals of the object.
So the almost, if you're just looking at the small subset, then you can mirror through these diagonals, but because this is not a square, the mirror would take a bigger angle to a smaller angle. But Switzerland has that symmetry you're talking about. Okay, so we've identified that there's, oh, perfect, yes. Yes, so these are different point symmetries.
I mean, there is a point symmetry.
Yeah.
I mean, homotechnical.
Oh, yeah, so you can take one point to another point, that's definitely it. So all of these do have mirrors as the common symmetry between all 6 of these flags is that they all have mirrors. And they all actually have different numbers of mirrors that pass through the sort of central points of their motifs. So I can show you that here, so. Pardon? So here Albania just has the one mirror dividing the double-headed, I don't know if it's a dragon or whatever. Georgia has 2 mirrors that meet in the center. Tennessee has 3 mirrors that meet in the center. Switzerland 4, Vietnam 5, and Macedonia has 8. And so the thing about these, this is great. So what we can do with these symmetries, so this is the, I guess, by like some of them have more symmetries, like Tennessee, you can have a rotational symmetry, but by area, this is the smallest unit cell that has a symmetry that's enough to represent the entire system. And so we call that thing a fundamental domain. So the smallest possible piece that we can identify symmetries to and complete the entire picture. So these are fundamental domains, and I'm sort of labeling them with some notation that we're going to use later. So star here means mirror, and then 3 means that 3 of them meet in the center. And so star 8 would be 8 mirrors meeting in the center here. And so basically, this little teeny wedge is all I need to do to explain like the entirety of Tennessee's flag. And so what do? I take this little wedge and I look at it like it's a stamp. And I pick it up and at a mirror, I flip it over and place it down and stamp it there. And then I pick it up and flip it over and stamp it down. And so basically repeating this set of operations is enough for me to get the entirety of the Tennessee flag. So, so here's something maybe a little more complicated. So here we don't have one central point, we have many possible points of symmetries here. So what symmetries do you see? Translation? Any other symmetries? Mirrors? Yeah, so there's many centers of symmetry throughout this. Yeah, there's rotations. So we've got all three of those symmetries here. So we can imagine a translation, we could take one floret motif and pick it up and move it over and translate it down. So that's a sort of big symmetry. We can look at rotation. So I guess I could imagine there's a rotation, say, here, I'll pick this one. So here is a rotation center. So I pick up, you know, this piece and rotate it over to here and rotate it over to here and rotate it over to here. So this is still kind of a big amount of space. But mirrors are interesting. So can someone start calling out where do you see mirrors in this picture? There's a horizontal mirror. I'm gonna draw them on the screen. So there's a horizontal mirror. Any other?
Vertical?
Yeah, there's a vertical mirror. Which
In the middle of the floret and on the red,
down the middle of the floor. Oops, that's a pretty bad straight line. And then one through here, and then I'll copy those over for the other. Yeah, so there's also diagonal mirrors, so passing through, I guess. Here's a diagonal mirror. Any other mirrors you see? Horizontal in the middle of the floret. I guess I should draw in the other diagonal here. Use words.
Just the other flower.
Oh, through
Flowers.
the diagonals through the rest of the flowers, okay. All right, I guess I can draw them down here as well.
When you say rotation and symmetry, it means that you might, if you had the letter head, it remains a letter head.
Correct.
But if you have a homothetic relationship of -1, you should split EF, right? Or don't. No, you don't.
So I'm considering rotations
It's the
to
same.
keep
I
the
just-
same
I
size.
just realized
Yeah.
that. Okay. Sorry.
Okay, so do we agree that these are all of the symmetries? Okay, so now we look and we've got some points here that are sort of distinct from each other. So there's this point here, and there's 4 mirrors that pass through this point. There's this point here in the center of the straight line. And halfway through the floret, there's 2 mirrors there, and then there's another 4 mirrors at the center of the floret. So that means that basically this pattern here, I can define one of these triangles. I can label it by the mirrors it has, and this is enough information to repeat the entire thing. And this wonderful. I'm gonna get rid of all of these so I can play the video. So this is wonderful software that's called Attractor, and yes, it is spelled that way. It's a Portuguese software, and there's sort of modern versions of it. This is sort of an older one that took drawings that were from all sorts of ancient architecture and things like that. So they were using that. So here's a video of how this sort of stamping process works. So here they've identified one of these fundamental domains, and they have, I guess, white on the edges is denoting that it's a mirror. So they can pick up this triangle and put it down on the plane, and every time they come to an edge, they can flip it over. And so this is enough to define the entirety of the plane. So this is this fundamental domain and the set of symmetries lets us recreate the whole pattern. So we've been talking a lot about so this is how I'm going to label it. So I've got a star 4, a star 2, and a star 4. So star just means mirror. And so for this, we're going to, I guess we can put this in whatever order we like, but typically we'll just order it from largest to smallest in this particular case. So this would be star 4, 4, 2. And that defines, that's the notation that tells me that this has a specific symmetry group. So here's another set of flags. And so I'm gonna put some caveats on these flags. So for, I guess, Maryland and South Korea, ignore colors. For South Korea, also ignore the striping in all of those boundaries. And for NATO, assume that the lines are all the same length. And I guess the UK is there's a little bit of other stuff going on. So assuming that with those caveats, what sort of symmetries do you see here?
Rotation.
Yeah, so there's rotations. Is there a mirror? Where's the mirror?
There.
Mirror. Where do I put it? So if these were squares, I could do that and mirror it, but since they're rectangles, like if you fold a rectangle in half, you get like a kind of mountain peak shape, not a perfect triangle, so you'll get something slightly different.
No, because
Yeah, so the coloring makes a mirror in NATO. So there's nothing else except rotations that people see here.
So Korea, you're in the middle. If we ignore the.
So this bit down here
Yeah, right.
doesn't have a. Yeah. So these have only rotations. Yeah, so Maryland does have some translations. It's a little hard to say what would happen without like knowing what the bigger pattern is. So if it continues like this, then I could say like, okay, this bit I can translate to here. But I don't know, like there's choices I have to make. So it's very possible, but involving choices.
Okay, have like this.
Which one?
Like this.
Not very close, but this is gonna come back to bite me later, but the stripe here and the stripe here are the wrong colors. So if we can, I guess we can agree that all of them have a rotation symmetry. And again, there's a center of symmetry for each of these. So, you know, Maryland would be here, NATO would be there, Hong Kong at the center of the flower. And the Isle of Man in between all three legs. And we can play the same game as we did before. So we can say, okay, what is the center of symmetry, and then carve out a fundamental domain. So here's the center of symmetry, and I'm using here shapes to denote the order of the symmetry. So for the twofold, like 180-degree symmetry, we've got some like diamonds. For the threefold symmetry, a triangle, fourfold symmetry, a square, and fivefold symmetry is a pentagon. So I'm assigning things based on that number, and then here I've picked places for my fundamental domain boundaries to be, but these don't have to be straight lines. It's just convenient for me to pick them. So what I'm going to do is now divide up one of these fundamental domains, and I guess we'll look at the Isle of Man because it's a pretty silly flag. And so in order to complete the pattern, I don't do quite the same thing I did with the mirrors where I could, you know, just flip them over. Here, flipping it over means that like a heel would be next to a heel over here. So I can't do that. So what I do instead is I cut along these lines and I roll it up like an ice cream cone. And so I put the center down here and I align the ice cream cone radially out, and then I just unwrap the ice cream cone all the way around, and that's enough for me to define each of these patterns. Yes.
Maybe the 70 degree is the 72.
Oh, 72. Yes, yeah, that is I cannot do the simple integer math I asked that you all be able to do. So yeah, sorry, that's a mistake on my part. You're correct. So how does this work with more complicated patterns? So this is now a 2D pattern, and this has a bunch of rotational symmetries. So where do you all see rotational symmetries?
Threefold.
Yeah, so the center of the stars, there's a threefold symmetry. Anything else? I'm just gonna draw one copy of these for now, because I think you all understand how it works with the like this point is the same as, you know, each of the other centers. Anywhere else you see rotational symmetry? Center of the tornado, so I guess this one? Yep, so what 6? Okay, so we've got a 6 here. In between the stars in the center, this one?
Yeah.
Okay, and what degree is that? Twofold, okay. So now we have a bit more information. I'm gonna draw in this threefold symmetric bit too. So what we have now are all of the rotational symmetries. We can use each of these along with the degree of rotation to define now a new fundamental domain. And instead of me miming this to you, I'm going to let the software, this movie play and show you. So here's one of those fundamental domains. And so here, the edges are identified and the gradient in them tells you how they map together. So here, it's gonna fold up, and then they're gonna inflate it. So this is now a samosa. And like we did with the flag, we're gonna unroll the samosa around each of these symmetry points. So it unrolls 12 times around the 6-fold, 6 times around the 3-fold, and 4 times around this 2-fold. And that's enough for it to repeat the entire pattern in the entirety of 2D space. So here we want to denote these again using symmetry centers. So we've got, these are not aligned with, okay, well, they're aligned with this part, but not the final one. So we've got a 6-fold center, a 2-fold center, and a 3-fold center. And so we're gonna use those to label this orbifold. And so before we had used a star to denote a mirror, and we used a star to denote a mirror because we have rotations that also have centers of symmetry. So we're just gonna say 6, 3, 2. And that'll, since we have a 6-fold center, a 3-fold center, and a 2-fold center. And that nomenclature is enough to define the orbifold with its symmetry. So what about this one? Yeah. Do I hear translation? Does anyone want to argue with that, or? everyone happy with it being translations? Okay, so this does in fact have translational symmetry. So we can rule out the fact that we have mirror symmetry because the orientation of the snake's tongues don't mirror each other. And we can also rule out rotational symmetry because then we have a snake's tongue going like this and then around like this and around like this. So in this case, we do have translational symmetry. And this is probably the one we're most familiar with, particularly those of us who are physicists and use periodic boundary conditions. And so in our movie here, we're gonna see exactly how periodic boundary conditions, how we would sort of identify one side with another side is gonna give rise to the full pattern. So here's our fundamental domain, and we're gonna identify sides together. So we'll start with the orange side and the orange side, so we'll roll those up, and the blue side and the blue side, those get rolled up, and now this whole thing is going to unroll its way around the plane. And so everything that's sort of touching the base is going to print the pattern out for us. So here's how this one works. So this is sort of an animation of how our the standard torus, the flat torus that we always draw with sides identified actually does lift to this full universal pattern. So there's some other symmetries we can have here. This one is not so obvious, and this is something that's called a glide symmetry. So it's got like sort of translations. There's some mirror. This one's confusing. And so here we're going to show that using a different fundamental domain. So this fundamental domain, I'm going to identify the blue side with the blue side, but here with a twist. So this now is a Mobius strip, and then there's a mirror line at its edge. So here it can wrap around the Mobius strip to get one side, mirror across the Mobius strip, and then roll back. And so this is a way of getting that symmetry combined. So using this non-orientable surface, which later I'm going to call a cross cap because historic reasons. But using this idea of using non-orientable surfaces is enough to create glide symmetries. So what about this?
Sorry,
Oh, yes.
can you, with a Mobius band,
Yeah.
handle symmetry where you have a different angle this way or that way?
So you can do
If the angle of the repetition was different this way from that way.
including the same mirrors or with. So you can have other types of glide symmetries where you have like a twist in one direction and then a twist in the other direction, and that gives you what's called void surface. And so that doesn't have the same like orientation necessary. So you can get this sort of translation, like rotation, like.
Hard to picture it, but.
Yeah, I actually tried to find, I don't have a copy of the original software here, because it doesn't run on like modern computers anymore, so I'd have to go dig up like an old MacBook from, I don't know, whenever I had a pre M chip Mac and try it there. So it's hard to see, and actually I don't think the animation does that well at showing it to you, but you can do more interesting things, and I'll show you in a little bit the combinatorics of what you can do.
Thanks.
So any other questions? No, okay, so we've got, oh, yes.
I'm sorry, but couldn't we just take like a piece of the doors and slide it
So I think this comes back to, like what the smallest possible unit is. So a lot of things, like I could imagine that there is a translation where I take, you know, this as my domain, and then I can just copy and paste that everywhere, and that's a translational symmetry. And then all of these have a translational symmetry baked into them. But that's just a larger domain, and there's symmetries within that domain. So if we want to like find the sort of smallest bit that has no symmetries remaining, is that kind of name of the game. So yes, absolutely, that is a thing, but we're gonna try to find the smallest one.
Thank you.
See. So we've got this dress, and there's, you know, we've understood symmetries pretty well up to this point. If we look at the bottom of the dress, I think we're pretty happy. We've got some obvious places. We've got some mirrors. We've got, you know, a mirror. Oops. We've got a mirror down the center here. Got mirrors through the centers of the blue stripes. At this center point, we've got a twofold rotation that takes this strip into this strip and this strip into this strip. And so we can kind of understand what's going on. And this would be, you know, mixing mirrors and rotations, but you know, I hope you will take my word for it that that's something we can do. But then we get to the top of the dress, and something really weird is going on here. And so in this dress, or in this piece of the dress, we have one obvious symmetry. We have bilateral symmetry. So it's just one mirror down the center. And away from this mirror, okay, things look pretty good in this triangle, but if I take, you know, something further out from one of these centers, like a piece over here, rotating to a piece down here, that's gonna start failing pretty fast. So we want to understand what's going on in the center. And so that leads me to curvature. And we're going to talk about curvature from the point of view of making clothes. And so this is a thing that I do in my free time. I like to sew clothes for myself and design clothes and things like that. So I'm going to sort of take intuition from that as a way of sort of building up ideas about geometry. So how many of you have sewn before, made any clothes? Okay, this is, I think, the smallest proportion of people that I've ever given a talk to. Okay, I think I saw 5 hands total. So maybe it would come as a surprise to some of you how this works. So if you want to make a shirt, I think I had this conversation with you earlier, but if you want to make a shirt, you might think, okay, well, you know, this is the shape of a shirt. So I cut out 2 pieces of fabric like this. I, you know, sew the front to the back and walk on my way. But no, the name of the game in sewing is taking flat fabric, so something that I can tile with those orbifolds I showed you before, and putting it on intrinsically curved bodies. And then even more than that, most of them have to accommodate the fact that we move in our bodies, that, you know, I can do this with my arms. I have to be able to have that mobility. I should be able to do a squat. I should be able to, you know, behave the way, like I don't want my body restricted by the motion of my clothing. So we need to accommodate all of those things into the design. Not only do we have to take our shape, but we also have to take the fact that our shape can change. So if I wanted to sew, in this case, a button-down shirt, like a dress shirt, this is actually what the pattern pieces look like. And this is very complicated. There's not just, you know, 2 or 3 pieces. There are dozens of pieces. And the other thing I think that's really remarkable about this is that there's almost no straight lines. And the straight lines that do exist are places that say fold, or maybe are the bottom of the shirt, because it's just going to be, you know, tucked into some trousers anyway, so the shape of that line doesn't matter. Everything else here basically has curved edges to it. And so these curved edges are the key for how we get curvature from these flat pieces into curvature that adapts to our bodies. And so we're going to talk a little bit about how that process works in this next section. And then at the end, we'll sort of, well, I guess I don't know what time I started. I don't know how much time I have left.
Can I get back to you?
Sure, okay. So, and then if we have time, I will come full circle and relate this idea of curvature to orbifolds, and I will tell you why we have 17 wallpaper groups. Yeah.
Unconstrained by time.
I appreciate that, but I will, everyone is very tired after the hike, so I'll try my best to keep it constrained. About 20 minutes, okay. Okay, so there's a couple of things that we do to add curvature to clothes. And the first one is a dart. So to make a dart, you take basically a flat piece of fabric, you fold it in half, and then you sew a diagonal line through it. So when you turn it back right side out, you've made a cone. So cone, you've sort of taken away material and you've added a center where there is curvature. The opposite of this is something called a godet, where you take a wedge of extra fabric and put it into a seam. So here I've added some additional area to my garment, and now I've created some curvature here. So where I have conical curvature here, I have here saddle-like curvature. So for this mermaid skirt, I'd have like a small amount of curvature around the knees, sort of pointing inwards, and then I'd have additional, like a larger amount of curvature going out. And so those are pointing in opposite directions. So locally that's making a saddle. And I can make this a little bit, I'm going to tell you an anecdote first, and then I will make it a little more precise. So this is my favorite paper. So the summer school I was at, 2 summer schools ago, one of the speakers put her favorite paper in a talk. So I figured I should start adding my favorite paper to talk. So this is my favorite paper. This is called Mathematics Applied to Dressmaking. It's by Sir Christopher Zeman. And basically the story of this is he went to a conference in Thailand, and probably in like the 1960s or something like that, and bought a dress length's worth of silk for his wife to have a dress made for her. And he comes back from the conference and takes it to the dressmaker, and the dressmaker says, "Oh, well, you don't have enough fabric. I need more fabric in order to make a dress." And he's not satisfied by this and says, "Well, I bought this lovely fabric, so I'm going to learn how to make my wife a dress." And so what he does is he starts learning from a mathematician's point of view how dresses are made. And so these are some models from his book. So here's a picture of someone's back. So you start with a curve on their shoulder, and then you have a curve for their waist, and then go around their bottom here. And so he said, okay, if I take a straight edge down and measure how much the offset is, I can divide that by 2, and then if I fold my fabric in half and cut it out, that should be something that would get an equivalent shape. And he says, well, I mean, that's just one place, and that's just only approximates this one direction of curvature, but we've got so many directions. So a mathematician would say like, oh, you need like infinite numbers of seams in order to perfectly match a body. But the dressmaker says, no, that's ugly. That's not what you want. So there's this compromise between taking the sort of mathematical idea of perfection and the dressmaker's idea of aesthetics, and sort of combining them into sort of a minimal set of seams that this is a good enough job. And so he sort of learns this process and eventually makes a dress for his wife. The other picture here is a picture from what that's telling a different anecdote. So he had a student, and they were doing topology, and they were interested in everting surfaces with punctures in them. And so she had proved a theorem that this is you can evert this structure. And then after she graduated, she went on and was writing patterns for a big company like Simplicity or Butterick or Vogue or something. And so she knew this, and so she's writing these patterns, and what she says is, okay, well, the things are inside out. You can sew the neckline together, then you can sew the sleeves together, then you turn it right way around. And in fabric, this fails. She's like, but I proved this theorem. But this theorem also relies on allowing curves on that surface to sort of contract to 0 points and to pass through each other and do some kind of interesting in surface deformation. So it turns out that real fabric, real seams, you cannot pass a seam through itself. So all of those instructions failed because the assumptions made in math were not the assumptions made in real fabric. But the moral of the story is he does in fact go on to make a dress for his wife, and then the paper ends with his wife reflecting on this whole problem. But it's a really lovely paper. It's really well written. I encourage you to check it out. So from, I guess, what he did, we can sort of look at these try to break down this idea of adding curvature into small units. So I told you that these are all based on darts and godets, and so I'll do this a little bit more mathematically. So I have here some material that has honeycomb symmetry. So this is a whole bunch of different mirrors. So I'm going to take 1/6 of it out. So instead of 360 degrees around this point, I have only 300 degrees. And then I can sew those edges, sew those two edges together, and I get a cone. And so this is, let's say I'll show it here. So I've got this one point here, and the object here, has perfect pentagonal symmetry. This is now a pentagon, but everywhere else I look, these are all hexagons. And so if I want to define curvature, I guess I've written it in the mathy way and said 2 pi instead of 360. So I'd take, I guess, 2 pi minus, I guess, the sum of the angles around it. So I have 60 degrees, 60 degrees, 60 degrees, 60 degrees, 60 degrees. So that's 300. So I take 360 minus 300. That's 60 degrees. So I have something that's greater than 0. So 60 degrees is greater than 0. So that's enough to define the curvature at this point. And for you soft matter enthusiasts, we call these disclinations. If instead I were to take that wedge and insert it into another piece of fabric, I have something very similar that happens. I end up with a point that has heptagonal symmetry. So I have 7, I have a 7-gon around this point. And from there, I can look at these other points, and these all have nice six-fold symmetry around them. But here, when I do the same counting, I say 2 pi minus the sum of these angles, or 360 minus the sum of the angles. Here I have 360 degrees, plus I'm adding in an extra 60 degrees, so I have 420 degrees. So when I subtract 300 or 420 from 360, I get minus 60. So now this point is now defined by minus 60 degrees of angle. And so this is from work with Lewis Campbell and Kelly Dell. And so this is trying to understand how to add curvature into flat pieces by bending seams. So here's just this puzzle piece that was drawn. So you can imagine just taking this and repeating it over and over, and you can get a scarf. So if I zoom into some little point here, I end up with on one side some angle alpha and the other side some angle beta. And since this is flat, these have to add up to 360 degrees. And I can add a little bit of angle to one of them. And so this adds a teeny bit of curvature to this point. So instead of just adding a teeny bit of curvature here, I can sort of add curvature all the way along the seam. And that's what Lewis did. So here are the two sides. Into one, I'm going to take away 60 degrees, but integrate it along the whole seam. And the other is plus 60 degrees, integrated along the whole seam. So here's what happens. And you can see that the shape of these is massively deforming, but the arc length isn't. So I'm keeping the length of it the same, just bending it away from whatever shape it was before. And now, and because the arc length is the same, that means I can sew them together. I'm gonna have seams that match completely along the entire thing. And so these are our new puzzle pieces. And so we can orient these in sort of different ways. So the first way we did was trying to take this vector connecting the starting point with the ending point and just making those two parallel. And so this is the puzzle piece, or this is not the puzzle piece, this is the sewing pattern we get. And so Lewis sewed these together to make a scarf. And so this is the scarf we get. So this clearly has saddle-like structure. So this has this like negative curvature signature to it. But it is sort of very symmetric. The other thing that we tried was, instead of these being parallel to one another, we can rotate them a little bit. And so we did that. And so this is the scarf that Lewis made with that. And this one is wonderful because this fits around like a neck and shoulders really well. So this one, you would assume that you would have sort of some sort of curved line like this, rather than having a wide shoulder and a narrow neck. You have, I guess you'd expect your head to your jaw to come out to the width of your shoulders, and then this would fit nicely. But that's not the case of people. So having this difference between the outer circumference and the inner circumference is enough to shift where that curvature is distributed. So we get something that fits really nicely around the geometry of a human body. And I have my own versions of these I made before or after Lewis graduated, but it's summer, so I don't have them with me here. But they do fit really nicely. Wait, you said 20 minutes and I didn't start at 5 more. Okay, so I'll be fairly quick. So basically we define curvature by taking some sort of vertex and subtracting the sum of the angles around it from 360 degrees, or here from 2 pi. And we can define whether a point has positive curvature, zero curvature where it's flat, or negative curvature just based on the sign of this number. So I'm going to do a little bit of arithmetic with these and see if we can come up with some interesting relations between these angles. So this will be I think the most boring slide, but stick with me to the end. It's got a kind of interesting result. So here I can rewrite this. I say, okay, what's the angular deficit per vertex? So I take 2 pi minus the angle, like the total angle per vertex. And I can then say, okay, what's the total angular deficit in my whole object? So now I say 2 pi times the number of vertices plus the sum of all angles in my structure. And we're going to do the same thing, except instead of focusing on vertices, we're going to focus on faces. So this is the other fact that I wanted you to know, is that basically the, I guess, angular deficit for a polygon with n sides is pi times the number of sides per face minus 2 pi. So it's something we probably all learned in like high school geometry and have since completely forgotten. I completely forgot it until I had to write the slide down. So we've got this fact now. Now we do the same thing. What is the total angular deficit in the shape? So I say, okay, so now I'm looking at faces. So I say pi times the total number of sides minus 2 pi times the total number of faces. And I'm gonna change this a little bit because when I have a side, then I'm kind of double counting what happened. So this edge here connects both this face and this face. I'm gonna divide this by, so this is so I'm, I guess, double counting. So this is twice the number of edges in my structure. So here I'm gonna say 2 pi times the total number of edges minus 2 pi times the number of faces. But now I've got two things that are equal to the total angular deficit. So now I can set these equal. So I have, I guess, 2 pi times the number of vertices minus 2 pi times something. I'm just gonna call it chi for arbitrary reasons that are historical. And then this I'm gonna set equal over here to 2 pi times the number of edges minus 2 pi times the number of faces. And so this gives me a relationship between 2 pi, between the number of vertices, the number of edges, the number of faces, and then some constant number. And so we end up with the number of vertices minus the number of edges plus the number of faces is equal to some number chi. And I'm not going to do the proof here, but there's a very simple proof that you can do just counting things on graphs, that this number chi is 2 minus twice the number of holes in your system. So we've used now basically counting to connect geometry, so the shape of each of these vertices, to topology, the number of holes. And then I'll just, I'm gonna skip forward a little bit and just tell you very quickly. So Euler characteristic is the number, this chi, so 2 times twice the number of holes. So there's a way of counting sort of orbifold features. So you start with a sphere, then you can do different things to them. And basically, if the orbifold has 0 or I guess Euler characteristic of 0, then it's planar. So any combination of these things where when I say cone rotation, then I'm saying like, okay, this is like 6-fold symmetric around that point. So then that would give me a 6 for A. So basically I can come up with basically some integer computations where I start with a sphere and then do any of these operations to it. And any way that those add up to be 0 gives me an orbifold that tiles the flat plane. So it turns out there's 17 ways to do this. So I'm just gonna skip through this bit of the slide and just sort of show you. This is made with software called iOrnament. So I drew a little flower, and then I can act on it with all of these symmetries. So there's 4 symmetries that are just cones, and I sort of drawn their symmetry centers in here. So the one we did before was 4, 4, 2, and there's a bunch more. We can do things that are just mirrors. So we did those. We've got here, I guess we did, oh, sorry, star 4, 4, 2 is what we did. And before the other one was 6, 3, 2. So these are all different things you can get with the same pattern. Mirrors and cones and rotations gives you some of these patterns. So these are very pretty. And then we have everything else. So this is just the combinatorics of everything else. We get things that have just pure translations. We get these sort of glides. I guess the glide and mirror is this one we did. There's, I guess, XX is the one that you were asking about glides that are not in the same orientation. So this is two like a twisted surface in one direction and a twisted surface in another direction. So that gives something topologically called like a cross cap or void surface. And so that structure gives you this. And then because I can tell you that anything that has no mirrors has some chirality to it, that means that anything that has a star, I can cross off the list of chiral groups. So here I have things that have rotations, I have these cross caps, glides and cross caps, and translations, and everything else is going to be achiral. So that means that I have a total of 7. Oh, sorry, that's supposed to be 7, not 17. So I have 7 chiral wallpaper groups left over, and this is what those are. And I will end the talk here. Sorry, I think I did run over a couple of minutes, but hopefully I've convinced you that there's this very nice language for understanding symmetries, which we call, I guess, orbifolds. And if you are curious how these symmetries work on like curved spaces, come ask me later. I have some slides to show you about that. But thank you so much.